So first and foremost, this is the same code that we kind of looked at in the last class, wherein you have a JPEG, and what we want to do is we want to change the sparsity and compress this image. So when you run this, you will line number 10. Yeah, this needs to. So when you run this, you will notice that you are gonna get the JPEG image, and then you will see its compressed representation. So this is the one image, and then you can actually plot the second image, and that will give you the the compressed representation. So if you do figure 2, you would get this compressed image. So ALO is nothing but the low resolution. So this ALO, we run the whole code. So line 14, I need to get this off. Then so these are the Fourier coefficients. As you can see, the most of the important Fourier coefficient are centrally located. So what we are going to do is we are going to remove all the sparse part, which is in the outside area, and then construct the image again. So let me see here. I'm 71. With my mouse. So you can actually run this code, and then you will see that once you have the sparse representation, you can actually reconstruct the majority of the images. Now, the next part which I want to talk about is, let me see, an example for the compressed sensing, and this example is very important. So what I'm going to do is I have this X signal that comprises of two frequencies. You have one with frequency 2 multiplied by 97, and the second frequency is 2 multiplied by 777. So what I'm going to do is I'm going to run in section. So let's run this, and you will get this image. Then what I'm going to do is I'm going to actually do a random sampling of the image. And after random sampling, I'm going to solve the sparsity problem to get the sparse representation. Now, what I want you to understand is this is the original signal that is constructed by combining those two signals. You have a slowly varying signal and you have a signal that varies quickly. When you combine these two signals, you get a signal which is of this form. Now, what I want to do is, I want to find out the frequency component in the signal. To find the frequency component of the signal, what I can do is I can actually send this entire signal and I would get the frequency and amplitude. Frequency on x-axis, amplitude on y-axis. Now what I'm going to do is, rather than sampling all the points, I'm just going to sample few key random points, which is nothing but the essence of compressed sensing. So what I'm going to do is, I'm going to start sampling these points, and then I'm going to use these sampled measurements to reconstruct the original signal. And when I do the FFT of the compressed sense signal, please understand, I am able to recover the frequencies and amplitudes in the original signal. Now, here is the practical application of it. Imagine if we are trying to do an infant MRI. MRI is sort of an image, two-dimensional image that is evolving with respect to time. So what we do is, rather than making that infant stay still or sedate the infant so that we can complete the MRI, we will actually use the principles of compressed sensing and take the snapshot where the period is varying and use that information to reconstruct the original image. And clearly, the reconstructed image does not capture the complete information. There is some loss, but still the reconstructed image is good enough for analysis purposes. Does it make sense? This is the compressed sensing in action. So what I want to do is, I want to quickly go through the code, and for this code to run, you need to have the CVX solver installed in the MATLAB. But this example is very important. So you have a signal. That signal has two frequencies. And now you are going to perform the fast Fourier transform on the complete signal. And then what you are going to do is, you are going to construct the PSD, which is power spectral density, on the whole signal. Now, next part is very important. What I'm going to do is, I'm going to randomly sample the signal. So I'm going to use a basis or a kernel that is randomly sampled, and I'm going to capture random snapshots from the original signal. And then what I would do is, I would build these matrices, psi, theta, and then I will solve the optimization problem using something called as the matching pursuit problem. So, and what I would do is, I would reconstruct the signal using these sparse measurements. And this is where you can actually find the PSD of the signal, original signal, and compare that with the PSD of the compressed sense signal. And as you can see, once you run this code, these are fairly accurate. Everyone understood this? The application of this is enormous. Imagine if you are going to do the speech synthesis. So basically you have some speech, and then what you want to do is, if you want to do the encoding, rather than performing the encoding on this complete speech signal, you compress sense the speech signal, transmit that compressed data, and reconstruct the data at the receiver end. Everyone understood this? Other approaches, imagine you have an 8K video, not 4K, 8K video that you want to transmit on a limited bandwidth data line. What you will do is, instead of sending all the data set, you will compressedly sample part of the data set, send that data set, and reconstruct the data set at the end. Everyone understood this? Now, some of you may say, what about this compression and decompression? If you do it in software, it's a tedious and time-consuming process. But you can build application-specific integrated circuits, like for example, chips that can perform this calculation. The chips that are specially designed to take the signal, perform compressed sensing, and send out the compressed sense data. And you can have a decoder, you can have an encoder, and you can have a decoder that will take that data and then reconstruct the original signal. So you can actually develop the hardware component, ASICs, that will perform this type of application. Non-periodic signal, yes. If you have a non-periodic signal, and I would actually encourage you. So here is my suggestion to you. This example, what you can do is you can convert this signal into a non-periodic signal. This basically signal time series, you can change, you can add some non-periodicity, you can add some type of randomness, you can add some noise, and then see if whatever you are running, if it is working. So I would encourage you to play with this example, and every speech or every signal or every picture or every movie is basically combination of signals. So you will have some periodic component, a periodic component, something like that. So please play with this. Just change this line number 9, and then try to capture the data. So that should give you a good understanding. The next part, what I want to do is, I want to talk about how it is done for the images. So if you run this, okay, so pad flip, let me see utilities. I need to add these files, EVX also, you need to add this file, the file. Okay, now let's run and see if it works. So what needs to happen is, this is actually how the compressed sensing works in the picture. So if you were to look at it, what you have is, these are the different solutions that are computed. So for an example, I just want to show you figure 5 and figure 6 are the solutions that are calculated on an image. So these are the coefficients or the weights that that actually are multiplying with these. So I want you to understand here, this line is completely filled with color. What that means is there is a non-zero weight there. There is a number there. So that number is represented by the color. But if I were to do a compressed sensing solution and try to solve the optimization problem, 0 here indicates, the white here indicates the weight is 0. Weight is 0. Weight is 0. So now what I have is, I have a sparse solution that is able to reconstruct the original image. So basically, this kind of gives you a visual representation of the solution. This solution is fully populated, those zeros. This solution has tons of zeros. Those are indicated by the white lines, white dots. Okay, any questions here?
Is the image just one column of the original picture, or it's already representing?
It's representing the complete two-dimensional picture. But again, I wrote the theory part of it in last class. You take a basis, you add either the Gaussian or Bernoulli type of noise parameters, and then basically you sample and then solve the optimization problem to find the solution using L1 norm. So basically the taxi cab norm or the Manhattan norm, and that gives you this solution. The previous number 5 and number 6. But ideally, what you have is you have the image that is fully populated. So you have a matrix, and then what you want to do is you want to find out the sparsest solution that can represent the key features of that image or the key data in that image. That is what indicates. Okay, any other questions? If you have any questions, please ask. The next part which I want to talk about is the something like the robust regression, and this is something we also talked about in last class. Imagine if you want to fit a line, but if you have outliers, then your line fitting will be incorrect if you were to use an L2 norm or the least square norm. But if you were to use the L1 norm or Manhattan norm, you can get a sparse solution, and that solution will be fairly robust. So if you once you run this code, I want you to see what happens. So now you will notice that you have few outliers. You can see you have few outliers. If you were to use the least square solution, what would that least square solution do? Least square solution will try to minimize the square of the error across all the points. Do you agree with me? And at that time, I want you to understand the red line is showing me the least square solution. It means I find out the error between the actual data set and the line, actual data set and line, square this term, keep on adding and take the first derivative and equate it to 0. That is how this least square solution, which is shown by the red line, is drawn. Everyone understood this? The problem here is this least square solution does not pass to majority of the points, because least square solution tries to minimize the error through all the points. So that's why it is not able to go through the majority of the points. But if you were to find the sparse solution, then you will realize that this is the sparse solution, or this is the L1 solution that is going through the majority of the points. Do you agree with me? So which means if you want to solve a problem wherein you want the system to satisfy most of the constraints, L1 norm is the right norm to use. Everyone understood this? That is what is the meaning of this robust regression. The next part is something called as lasso, and I need to discuss what lasso is. So I'm gonna kind of go on to my whiteboard. And let's discuss what lasso is. So lasso is a very famous approach. So parse regression is L1 norm may regularize statistical regression. So what we do is we actually do something like least absolute oh, yeah, I know different page visible, but I don't know why that different page is visible. Just a second. Okay. So least absolute shrinkage and selection operator, which is called as lasso. So this is also called as penalized regression. That balances model complexity with uh, basically descriptive capability. So if you look at the classic problem, AX is equal to B, this is the problem to be solved. But this system is overdetermined, which means it has more equations than number of variables. So it has more equations than number of variables. Today is not a good day for Zoom. Unfortunately, today is not a good day for Zoom. My apologies. Yeah. Okay. Okay, more equations than number of variables. So this equation can be written as x, find the values of x such that you have argmin of x, which is the minimum argument of x, which is given as the absolute value of ax minus b, which is the least square norm, plus lambda is equal to x1. Now, mathematically, what this means is you are trying to find out the certain values of x that satisfy this equation. And now I want you to understand what this equation physically interprets. The physical interpretation of this equation is, if you look at this is the least square solution. But this least square solution is penalized or corrected by a factor lambda. And the way this problem will be solved is the value of lambda will be varied for multiple from range, given range in the algorithm. You can set that range, and then it will try to find out the appropriate values of x. So this technique is a statistical technique approach, and this is very commonly used in statistical analysis. So what I'm going to do is I'm going to show you an example wherein MATLAB will perform the lasso regression. But there's one more point which I want to talk about. So extension of lasso, extension of sparse regression is sparse representation. So sparse representation means if you have a data, then and you have this something called as similar to SVD. So this is the data matrix. This is the data. This is two-dimensional data. And then you can actually construct a lower dimensional basis for representation. So you can actually do a low dimensional basis for the representation. Now, we actually talked about SVD. We also talked about the principal component analysis, or something called as the PCA. So what we do is for PCA, we take the data, we subtract the mean, and then we perform the SVD, and that gives us the principal dimensions where that data is sort of scattered. Now, the problem with principal component analysis, or PCA, is it is also very sensitive to outliers. For an example, if your data has tons and tons of outliers, your PCA is not going to give you an accurate result. So principal component analysis would fail if you have the data that has a lot of variability or variation. So what has happened is, using the concept of sparsity and essentially sparse representation, there is something called as the robust principal component analysis. So robust principal component analysis is also called as RPCA. So here is the basic idea. You initially have this data matrix. This is two-dimensional data matrix. So this data matrix X is kind of separated or partitioned into L plus S, where L stands for the background and this is something called as the foreground. So, and L is structured low rank matrix L, and S is actually a sparse matrix. So if you want to solve this robust principal component problem, what you do is you basically set this problem up as an optimization problem, something like minimum LS rank of L plus subject to L plus S is equal to X. So please try to understand, to solve this problem, what we need to do is we need to find out the values of L and values of N in such a way that the L achieves the minimum rank with a zero norm on S. Now, this is a mathematical way of representing how to solve the equation. Now, even though we can represent that mathematically, to solve this decomposition problem. Now, I want you to understand there's a math part to linear algebra and there is application part to linear algebra. So, from linear algebra point of view, what it is, I have this matrix X, and the problem with this matrix X is the data is scattered. Everywhere the data is scattered. Typically, that would happen if you were to solve the Netflix price. You will have the data that is scattered. There is a lot of variation. If you perform a principal component analysis, or even if you perform some type of machine learning, that will not give you good results because of the variability and variation in the data. You will not get consistent features because those features are spread across. So to solve this problem, what we want to identify is we want to identify the part L of that data, which is a structured low rank matrix L, and then A plus S, which is the sparse matrix. In other words, you have this data, somehow you want to filter out or you want to separate out signal from noise. That is what Tuli is doing. To do that, you need to find out the values of L and S. And how would you find these values of L and S? The condition, the constraint is L plus S is equal to X, which means the total data should be comprised of signal and noise. But to separately find signal and noise, we need to find out, we need to have this condition, which is a minimum rank condition. So what does it mean by minimum rank condition? It means what is the lowest dimensional representation of the data? In other words, if you have this huge data, what is the smallest matrix that I can use to capture the key features of the data? So that is what is this minimum rank approximation. And everything else is junk. So that gets separated. It's actually in zero norm, which is part of the S. That is what it means. Now the question is, how do we solve? We know that this is the way the problem has to be solved. That does not mean we can solve the problem. It appears to be like because of this minimum rank and this zero norm condition, this problem cannot be solved. This is something called as computationally hard problem. So what we want to do is we want to approximate this problem into a problem that we can solve, that we can computationally solve. And that approximation problem, so what we do is this problem is approximated as minimum of L and S, L star plus lambda S1 subject to L plus S is equal to X, where we define this something, a special norm, which is called as nuclear norm. And some of you may ask me, what is this mathematical jugglery? At the end of the day, what we want to do is we are not going to solve these problems by hand. We are going to write the MATLAB code or maybe R code or Mathematica code or Python code to solve that problem. What this means is if I were to write the MATLAB code to solve this problem, it will take infinite amount of time to find out values of L and S. That is what it means when it is a computationally hard problem. However, as soon as I change this minimum rank condition to a nuclear norm and add a regularization parameter, or essentially the Manhattan norm or L1 norm, this problem can be solved in finite time, which means I can write the code inside MATLAB or inside Python that would actually solve the problem. So if you are a hardcore computer scientist, or if you have taken courses in computer science or theory of computation, there is P is equal to NP, that type of a problem defined. So which means if you have a mathematical problem, if you want to solve that mathematical problem with a numerical technique using computer algebra, the first and foremost question you have to ask, is this problem solvable? If that problem is solvable, then you can write a code in Python or in MATLAB or in C or C++ to solve the problem. But if the problem, the mathematical problem itself is not solvable, then no matter what you do, the problem, no matter what type of software you use, that you won't get a solution in a finite time. So that is P is equal to NP problem. And what we do is to attempt problems like that. This is basically a non-convex problem. So to do that, we approximate it to a problem which will give us not the exact but approximate solution, but that will be good enough for practical purposes. And that is what this represents. So what that means is we are going to solve this problem using MATLAB, but it is not possible to solve the original problem using any computer code, but this approximate problem can be solved. And next thing is you have to specify two important conditions on these matrices L and S. The first condition that you want to specify is L is not sparse. You can't have a sparse matrix and another sparse matrix. You can't have two matrices with bunch of zeros. So L is not sparse. And second, S is not low rank. The entries are randomly distributed. So if you were to solve this problem, you can solve this problem using the MATLAB code. The last part, which I want to touch upon briefly, is sparse sensor placement. And then I will show you the code. Now, what is this sparse sensor placement? Imagine you have a machine, or let me give you an example, human body. You want to, basically human body is going through a lot of physiological and biological processes. It is not possible for us to measure each and every biological process or physiological process. So exactly what should we be measuring so that we get the detailed understanding of all the physiological interactions that are happening inside the human body. So what I want to emphasize here is sparse sensor placement is how do we capture the most important piece of data, most important information from a machine, from a picture, from a signal by placing the sensors at key locations. So in other words, if you want to measure the health of a person, you are going to measure the body temperature. You are going to measure the respiration rate. You are going to measure maybe something, the pupil dilation, something like that. So where do we place sparse sensors? So how do we measure the processes with the least amount of sensors that are possible? So that is the problem which is called as the sparse sensor placement. And where would we put these sensors? Where would we put these sensors? So this problem is kind of written as you have this y is equal to c psi r a, and that can be represented as theta times k. So this sparse sensor problem is nothing like finally reduces to construct a sparse measurement matrix so that this inversion is well conditioned, which means the inverse actually exists. And this is basically the application of sparsity and sparse signal processing. So let me now show you the code. So what we are going to do is we have the phase data, and from the phase data, we are going to actually all phases.mat. So let me see if I have data for some, yeah, I have this data. So all phases.mat. P. And I would encourage you to run these codes and try to see. So now what you will have is we are running the same logic on the Yale data set. And what we are going to do is we are going to actually reconstruct the sparse representation, and you will realize that you can actually collect a piece of the new face and then look at the similarity between the feature of the new face and the feature of the data set. So basically, I'll kind of go through this code step by step, and then we can actually run this. So first we have this all faces.mat, which is the Yale face data set. We load that into this. Then what we want to do is we want to actually separate out the data set into the training data set and the testing data set. So I have 30 training data set and 20 training data set. And then basically what we do is we go through this for loop, we load this data, and then what we do is we actually perform the downsampling of the training data. And the purpose of the downsampling of this training data is to build this matrix theta. And then what we do is we do the renormalization. And after renormalization, what we have is we now take out some of those faces, some data set, and then try to corrupt the data set. So what we are going to do is basically you take the image and on top of image you add a mustache. And it may not be apparent here what this is doing, but I'll tell you a classic application that FBI uses this technique. Imagine FBI has the data set of faces. So if you go for a visa or you go for interview at consulate, they will take a picture, they will take a biometric. So your face changes over time. So now if you see a picture of a person without glasses, and if you see the picture of the person with glasses, how do you know that the face without glasses is same as the face with glasses? For example, if I went for visa, they took a picture and I have mustache. And after a few days, I shave the mustache and try to go through the immigration again and they take the picture. Now, how do they make sure that this image without mustache is same as the image with mustache? So for that, exactly that transformation we talked about L and S. So you have this image, which is X. You want to separate out an L from S, where L contains all the important feature and S, the sparsity, contains all the noise. If you use that algorithm, even though the person is wearing glasses, or if whether the person is having mustache, that data set that is related to the glasses or mustache will go as part of the sparse matrix, but that L matrix, that the core data set, would remain as is. What it means is you would be able to compare these two images, where one image is seemingly corrupted. I mean, you may not be at human eye level, you may not be able to see the image, the similarity between the images. But as soon as you distill the data through this algorithm, you'll be able to find out the core features from the original data set and from the new data set. So that exactly is being done here. So you capture the image of that person, then add a mustache, and then what you do is you basically rerun through the downsampling algorithm, and then at the end, what you do is you do the L1 search, and this, believe it or not, what this is the norm condition that we wrote. And this norm condition can be solved in finite amount of time, and that gives me a basis for comparison. And then it shows me that yes, my the picture with the mustache is same as picture without the mustache. So I would encourage you to run this code and kind of try to see and verify yourself that data is the same. The other thing is, imagine you have image of a person and you get a blurry image. How do you know that the person in that blurry image is A or B or C or D? Same algorithm. You run that through the algorithm, do the regularization, separate out the L from S, and you will realize that you'll be able to get a very good correlation between the blurry image and the actual image. Everyone understood this? This is extremely useful to find hidden patterns in the data. So you have all this data and you want to find out, and there is something else. There are some coherent structures. So what happens is, believe it or not, statistic plays an important role in normal life. You have this huge data set, or that data set could be daily activity. That data set could be the habit of person. That data set could be the movies that we watch. That data set could be the foods that we eat. Every data set has hidden coherent structure. So there is a structure that is coherent, that is constant. It is not possible for humans to understand that coherent structure on the data because the data itself is so huge. But with these statistical techniques, you can find out the coherent structures that are present in all the data set. For that matter, if you look at the turbulence data is very complex. It also has a coherent structure. If you look at the foods that we eat, or other thing is the disease and the genome identification, you will notice there is also some coherent structure. And depending upon the energy levels, it could be Lagrangian coherent structures and so on. But those coherent structures, these data analysis techniques that are based on the linear algebra can identify those coherent structures. So I would strongly encourage you to run this code and then try to get the result, and please verify yourself. These codes they can be used even for your research application. For example, compressed sensing code that are used to analyze PPG data, because say you have a sensor and that sensor has limited capability, limited memory limitation or bandwidth, and you still want to capture the physiological signal that is super complex and changing, then you can actually use the compressed sensing technique to get the data point at key locations, so that eventually, if the need be, you can reconstruct the entire signal. So please run this, and I would encourage you to run this. I actually suppressed some of those figures, but if you really want to understand the code, my strong recommendation to you is look at each and every figure and verify it yourself. Now, the last part is, imagine if you have the data set wherein there is too much variability. So variations are quite huge. So in that particular case, you can use something called as the robust principal component analysis. And once you do the robust principal component analysis, you will realize that even if your data has too much variability, too much variance, you are still able to identify the principal components. Let me give you, and this will take some time to run. Let me give you a simple, say if you want to run a machine learning algorithm, what is the basic requirement to run a machine learning or deep learning algorithm? You need to have good data so that you can identify the features. But now, if your data is too much spread, or if there is too much variability, it is not possible to find out the important features of the data using principal component. However, if you were to use the robust principal component, you are still able to acquire or still able to identify the most important features in the data. So again, this gives you an example wherein you have the data set, and what you are doing is data set has a lot of noise and lot of variation. So you can perform the robust principal analysis, the robust principal component analysis, and find the most important features. On the other hand, if you were to perform just the principal component analysis, it's not going to give you the results, or you will not get the sufficient features that are important for classification or for analysis purposes. So I would strongly encourage you to run this code, and I would encourage you to read the relevant part from the textbook, where some of these codes are explained in more detail and more detailed math is discussed. So with this, we have finished chapter 3. Next chapter, and we kind of finished entire part of the chapter. The only thing that I did not cover is basically some math part that is in here, but that is self-explanatory. Once you read through that, you will be able to understand that. And we will start with the next chapter, which is regression and model selection in next class. And that eventually would segue into machine learning and deep learning. So far, we have finished first 3 chapters, or the first part, dimensionality reduction and transform. And then we are going to start the machine learning and data analysis. So the basic machine learning is regression. So first we are going to talk about regression. Then we are going to talk about the Pareto front. We are going to talk about the model selection. And then we will talk about the, again, supervised, unsupervised learning, support vector machines. Then we will talk about the neural network and deep learning. And then we'll move on to the dynamical systems, balanced models, data-driven control, reinforcement learning, and so on. But once again, please read the book, and if you get time, watch the lectures. Again, Steve Brunton, the author of the book, has created some excellent videos. I would encourage you to review those as well. With that, I'm gonna stop here, and I would be happy to answer any questions that you may have. And sounds.zip. So let me ask you this: on the previous assignment, everyone